All right, it's 3 o'clock, everybody. I will try to stay on time here. My name's Chris Fonnesbeck. I work in baseball operations and player development for the New York Yankees, though I live in Nashville. We are hiring, by the way, particularly if you're a data engineer. We'd love to hear from you. I'm going to talk today, obviously, about Gaussian processes. First, some boring technical stuff. If you haven't seen the repository already, here it is. Don't worry if you haven't. You don't have to do everything hands-on, but you can if you want. It's github.com/mylastname/gp_regression. There are instructions on installing a conda environment, etc., and so on the README page. If you did install it already, you might want to look at it again, particularly if you're on macOS Catalina. I have run into problems with the new version of macOS with some of the GP stuff. But if all else fails, I've got the happy little launch binder button here. So you can spin up a machine remotely, wherever binder exists, and run it that way. Or you can just sit back and relax and enjoy like a lecture sort of thing. So it's up to you. But these I won't move this repository. It will always be here for you. So how many here have used Gaussian processes before in their own work? Okay, good. How many people have used Bayesian methods in their own work before? How many people have used PyMC3 before? Okay, this is perfect. All right. Let's get going then. My original plan was to do a whole bunch of notebooks, and I changed course kind of at the last minute. And I sort of have a hybrid approach here. So I'm going to, because a lot of this stuff is expository. Is that the right word? Didactic. So, and I think slides are better for that sort of thing. And then we'll switch over to particular notebooks when we need them. And the idea here is to give you a little bit of background and then give you some hands-on building GPs on your own, just to give you kind of practice. And I probably have more examples than we'll go through, and that gives us a little flexibility in case we run, short or long on time. So please interrupt me and ask questions. GPs aren't the easiest topic in the world to understand the first time round, even for very smart people. So it took me 5 or 6 times before I really got it. So even if you leave today not knowing quite what they're all about, don't worry. It's not you, and it may not even be me. It's just a hard topic. Okay. What we want to do here is to give you some methodological practice and some implementation practice. This isn't a theory course, even though you will see math, and I will explain all the math. But do ask questions if anything is not understandable. Okay. So the reason we're talking about Gaussian processes is that they're very useful, like Bayesian methods in general. They're a very flexible method for doing nonlinear regression and classification, though we won't talk much about classification here, in a whole bunch of settings. And it's it is a class of Bayesian nonparametric models. And like I said, it's a large topic. We're not going to cover it all in an hour and a half. This is just going to be a sort of a quick introduction to them. So again, the motivation is kind of in their utility, right? It's the fact that there's a lot of messy data out there. I've spent most of my life dealing with large observational data sets, which means they're very noisy, they're very nonlinear, there's missing data, and the default approaches for statistical methods are often not suited for that messiness, right? So if you look at a textbook example, so this is from I found a textbook example of regression. This is what you get, right? The points are already lined up for you, and you just got to draw a line through it. Simple as that. So this is regressing, looks like reported weight on measured weight. See, people lie about their weight or something. And those are the sorts of examples you get. You feel good coming out of class, and then you go look at real data, and nothing works, and it makes you sad. So real data looks more like this, right? So we've got some of these are baseball examples, actually. So this is the swing speed of a bat against the path angle of the bat, not linear regression there. This is a factor over time. I'm not sure where that one came from. These are marathon data, marathon timely, having just had the New York Marathon here. This is the Boston Marathon, a histogram of their of finishing times. Another baseball example where it's highly nonlinear. Okay, so real data kind of looks like that, and we want methods for dealing with it. So I'm going to focus on applications to regression analysis. I assume a lot of you have seen regression before, so just one or two slides on really what regression is. This is kind of the most general form of a regression model, right? It's you're making predictions about some outcome y conditional on a predictor variable or set of predictor variables x. And so g in the general form can be almost anything. The simplest form is this linear regression model. So if x is just a matrix of predictors times some regression coefficients, it's this, right? It's an intercept plus a bunch of slopes. That's kind of like the example I showed you before. The very simplest one, the univariate linear regression. And so these are kind of the default assumptions, right? This is kind of the default approach to analyzing data. Just start with a linear model, linear relationships among the variables, and the other important assumption is parametric distributions for data, almost always normally distributed, right? So the idea here is you make a prediction based on the predictor variable, and the difference between the prediction and the observation has this normal distribution centered on 0. And sometimes that works, sometimes it doesn't. These things generalize, but this is an example we're going to see in one of the notebooks. This is spawning salmon and the number of recruits that they get. And linearity holds in some places and not others. But we can generalize linear models. So there's a general form is generalized linear models where g is some other function other than identity, and maybe the parametric form of the distribution of the data is not normal. So common ones here like logistic regression, right? So if you've got failures, the zeros, and successes, the ones, and you try to draw linear regression, you'll get this weird line like this, and it's not very good at predicting anything. So now we transform it. We do this logit transformation, right? So this is the inverse logit. So it takes this linear stuff and it puts it on the scale of 0 to 1. And so you're modeling the probability of a 1 instead. It's still a linear model, actually, even though that's nonlinear, because it's still linear in the parameters. Another way of dealing with nonlinearity without leaving generalized linear models is to do polynomial regression, right? Where even with one predictor, spawning salmon again, we could take number of spawners squared and add this polynomial term, make it quadratic. We'll actually do this in the hands-on example. And you can go crazy. The more polynomial terms you add, the closer fit you'll get to the data that is used to fit the model. And we call that overfitting, right? And so implicit in this is another step you have to do, which is model selection. You got to pick the right size polynomial that is neither too underfit, like the linear example, or overfit. That's a 15-degree polynomial on the other side, almost certainly overfit. Okay. Whether or not you do linear models or nonlinear models or generalized linear models, you have another choice to make, which is what set of methods, what paradigm do I use to fit these models? And we're going to use Bayesian methods here. And this is when we talk about probabilistic programming, which is one of the newest buzzwords in data science. It really just refers to numerical methods, computational methods for doing Bayesian inference. And the reason it's called probabilistic programming is that Bayesian methods make inferences and predictions based on probabilities. So everything in Bayes is a probability distribution, and you manipulate probability distributions to get answers. So almost any model that you can build in a classical sense, frequentist sense, we probably all took more classical statistics in college if we took one, even if you're not a statistics major. Unless you went to school very recently, they were probably always frequentist methods. You were learning about t-tests and ANOVAs and regression. You can do all those things as a Bayesian. Okay, there are Bayesian versions of almost everything. Okay, so I'm going to quickly describe some Bayesian methods just to make sure everybody has the same baseline of information. This is a part of Bayes' formula. These are the interesting parts of Bayes' formula. And what you should notice is that the thing that we're estimating over here is a probability. So we're saying the probability of theta given y, where theta are the things that are unknown. That's anything in your model that's unknown. So it could be regression parameters if we're building a regression model like we're about to do. They could be hypotheses. They could be missing data. They could be predictions. Anything you don't know, you can put into a Bayesian model and estimate it. And then y are the data. So our inference is, what do we know about theta after having observed y? And the way that we do that is we combine what we know about theta before we observe our data with information from the data. So there's kind of two pieces here. And these things have names. We call this the prior distribution because it's before we saw the data. This is the likelihood function. Bayesian inference obeys the likelihood principle that says all information relevant to the unknown parameters in your model are contained in the likelihood. And that is combined to get a posterior distribution. Okay, so, but you'll notice there's no equal sign here. I didn't write an equal sign. I wrote this symbol here, which means proportional to. It's equal to up to a constant. And so what it's missing is a normalizing constant below that guarantees that this is a probability. So probabilities go in, that's a probability. That's not a probability. And so we have to scale it. And so the problem is that that's the hard part. That's the least interesting part, but it's the hard part. And this is the part that's made Bayesian inference really, really difficult. The denominator is just the numerator integrated over all values of the unknowns, theta. So you integrate out your unknowns. So we call it the marginal likelihood, actually. The reason it's difficult is that theta can be pretty big, right? There can be lots of parameters in your model. Even the regression model, the simple regression model that we're about to fit, has 3 parameters: an intercept, a slope, and a variance or standard deviation of the error, right? That's a 3-dimensional integration. I can't do that. I can do 1-dimensional sometimes. 2, if you give me the right easy formula. 3, forget about it. Okay, most of the models I build have dozens to hundreds of variables. So you just can't do this in closed form, except in very special cases. Any questions about Bayes so far, by the way? I know some of you have done this before, so this is a boring review, but anything need clarification? Okay, that's the idea. That's really all I'm going to talk about in terms of Bayes. The whole point is calculating these posterior distributions. And happily, today we have lots of ways of doing that. In general, we even have lots of ways of doing that just in the context of Python, since this is a PyData conference. In fact, there's a Stan tutorial going on right now. And so I'm going to use PyMC for a couple of reasons. One is I'm part of the development team. 2, it's a really easy way to learn Bayesian inference because it's a very high-level probabilistic programming language. Okay? It kind of hides the complexity of the Bayesian methods. It certainly hides the numerical methods that are used to fit that. So we're not going to concentrate on what MCMC is and all that stuff. We're going to kind of just assume that for the moment. We're going to concentrate on how to specify Gaussian process models, and we're going to do it through PyMC. This was started back in 2003 when I was a postdoc, and it's based on Theano. And Theano is, pour one out for Theano. It doesn't really exist anymore. It was a, well, it's still there. You can still find it, but the project is no longer active. It's a framework for doing deep learning, essentially. And The reason what we've done is we kind of hijacked that deep learning engine to do probabilistic programming because A, it's a very powerful computational engine, and B, it does automatic differentiation for you. It calculates gradients automatically. And the reason we need that is that in PyMC, we implement what I would call next generation Bayesian inference methods. And those methods rely on gradient information to help you get a better idea of what the posterior distribution looks like. So we're going to be using methods called Hamiltonian Monte Carlo and NUTS, which are all gradient-based MCMC methods. And it's a NumFOCUS sponsored project. And you should all have it installed on your computer. So let's do the first hands-on. And so if you're doing hands-on, I will do it here too if you're not playing along, so you can watch. So one of the notebooks in the repository is called spawningsalmon.ipynb. Let me just open that up. Let me this. And I've opened it up here already. I think I saved them to the repository unrendered, but I will clear out everything here. Can we see that at the back? What is the repository? It's my last name. It's github.com. / my last name / GP_regression. And there's a binder hub tag on there, and you can actually run it in binder if you don't want to do the whole installation thing. Okay, so this is the example that I showed you already. So this is spawning salmon. And what we're going to do so the goal here is twofold. We're not going to do GPs quite yet. We're going to build a regular regression model, but we're going to do it in a Bayesian approach using PyMC. So it'll give you exposure to regression and to PyMC. So building any Bayesian model, no matter whether it's non-parametric or not, or parametric, it's kind of a three-step process. 1, specify your model. 2, calculate posterior distribution. And 3, check your model. So the first step, specifying the model, is really here. So we write this down and we turn it into code. So this is the same regression that we saw earlier on, right? Linear regression with normal errors. And so what you have to do is figure out what your priors are and what your likelihood is. So remember that unnormalized Bayes formula. We have to specify the right-hand side of that formula, the likelihood and the priors. And so in this model, we have 3 unknowns, beta naught, beta 1, and sigma, and 1 likelihood, which is the normal distribution, which is where the data goes in. Okay? And so what I'm going to do is specify 0 mean normals with a standard deviation of 50 for the betas, and a half normal with a standard deviation of 50 for the sigmas. Why did I choose those? Because I like those numbers. They're just reasonably large numbers. They're not too big, they're not too small. Part of model checking is you go back and see whether those are good assumptions. But the idea is you go, how big could it possibly be in the biological constraints of salmon spawning, for example, right? And how small could it be, for example? So these go up to positive and minus 150. We're pretty sure they don't go higher than that for either of those values. And then here's my half normal. So it's just the absolute value of a normal, essentially. Okay? So those are my priors. Here's my data. And then a PyMC model looks like this. I'll quickly explain, give you the tour here. PyMC3 uses this notion of a Python context manager. Context managers are usually used to manage network connections and files and things. And it takes care of all the business of opening and closing connections, a few other things as well. What we use it for is to build our models. So rather than have, instantiate a model and say, add this parameter, add that parameter, add another parameter, which is fine. It's just a little verbose. So what happens here is any PyMC object that's created inside this context manager is automatically added to the model. Yikes. Little hiccup, hopefully. It's coming back. I didn't touch anything, I swear. OK, there it is. OK, so the nice thing about, I think, about PyMC is that what you write down in code looks a lot like what you write down on the whiteboard, or in Markdown in this case, right? So here are my priors. There's a beta, normal, mean 0, standard deviation of 50, and then I do shape equals 2. I could have beta naught and beta 1 as separate normals. This is just more compact. Okay, and then my half normal, the same. And then I can just straight up calculate this deterministic. So this mu is just a deterministic linear combination of the data and the parameters. And then here's my likelihood. And likelihoods look a lot like priors, don't they? It looks very much the same thing. The only thing that distinguishes it is this observed argument. So these things have been observed, so they're fixed. Remember, we condition on y. This is our conditioning statement. It says we've observed this node, so don't change the value. Right? Observed things don't change. They're no longer random. So everything else is treated as random, and that's fixed. Okay? And that's it. That's the model. I already ran it. OK. All right. And then once we do that, we can press the inference button, as one of the PyMCers, Thomas Vicky, likes to say. This is where we hide everything from you. So we can fit this using Markov chain Monte Carlo just by calling sample. OK. And nuts is the algorithm that it's using. It's an auto-tuned version of Hamiltonian Markov chain Monte Carlo. And so, but don't worry about that. I'm going to sample 2 chains. You should always do at least 2 chains for model checking purposes. OK, and I ran it for 1,000 iterations, tuning it for 2,000. Probably didn't even need that many. It's really, Hamiltonian Monte Carlo is very efficient. OK, and we can look at the output. OK, so there's the estimate of beta naught, about 60. Slope of about 0.53 or so, and then sigma. Okay. And then the nice thing is that we can now sample. So everything. This represents the posterior uncertainty in those parameters. If we collected, if we had millions of observations of spawning salmon, these would essentially be point probabilities with no uncertainty around them. So as we get more information, these things kind of collapse to a point. So it's not the distribution. It's not that we're saying these things are random and they can be 40 on some days and 80s on another. It's a particular value. We just don't know what it is. So we're using probability here to express our uncertainty. Okay. And then we can sample from that. We can sample candidate true regression lines, right? But this is forced to be linear. Okay. So sort of squint at it, it kind of looks a little nonlinear because of where the data is sitting, but these are just straight lines. All right. And then, as we said, we can generalize this to a quadratic, or like a polynomial model. We'll use a quadratic. So with a quadratic, we're just adding another x2 term, right? We're squaring the spawners and adding it to the model. So this is exactly the same as the previous one, but with two changes. One, we have 3 regression parameters here instead of 2. And here's where we add it, and it's x squared, which is the other term. And so now we have a quadratic model. We run it just the same. Has a little more trouble with this one. Now it's found it. So it does a bunch of tuning, so sometimes it can be slow initially. OK. And now we have one that's, a somewhat better fit than the last one. Okay. We might try cubic term or something like that, or you could use a totally different model structure if you wanted to. Okay. Any questions about PyMC model building or regression? Okay. All right, we're going to go back to the slides for the moment. You can leave that open because we're going to use this data again. to unmirror my, there you go.
I was curious how you type in those Greek letters.
Oh, sorry. Yeah. So that's the magic of Jupyter, just like LaTeX. So \alpha, A-L-P-H-A, and then you hit tab, and Jupyter magically turns it into, it's the magic of Unicode.
Cool, thanks.
So they're just LaTeX characters. OK. All right. So that's regression and Bayes. Now, on to why we came here, which is GPs. So what we're going to do here is build flexible nonlinear models with Gaussian distributions, with normal distributions. And this doesn't seem like a very good idea, right? Because we've seen what normal distributions look like. They're symmetric. They have very narrow tails. Everything's really close to the mean. It doesn't seem particularly flexible for modeling messy data. Well, it gets better when you have more than one of them. So the normal generalizes to the multivariate Gaussian or the multivariate normal. So this is the bivariate case where we have two elements, right? And so we have, rather than a mean and a variance, we have a mean vector and a covariance matrix. And the important thing is that so these are just the marginal variances for y1 and y2. But the important thing are these off-diagonal elements, which is the covariance, which includes this correlation term here. So it's the correlation between y1 and y2. And it determines, how much we know about y1, for example, given the value of y2. They're more closely related to one another. So so rho goes between 0 and 1, where 0 is completely uncorrelated, and 1 is completely correlated. Okay? There are two important properties to Gaussians that make them very handy for building nonparametric models. The first is the fact that it's really easy to marginalize. And what we mean by marginalize is when you have a big multivariate Gaussian with hundreds of elements, n elements, and you only want a few of them, it's really easy to get rid of the ones you don't want, marginalize them out. So let's say x and y are not just two values. Let's say it's a whole array of values. Say we only want half of them. We just want to get rid of y. So we have to do this, right? We have to integrate out y, which seems, I just finished saying how hard multivariate integration is, right? But if it's a normal distribution, it's really easy. You just cover that up, and you cover these up. And all you do is you pull out that top quadrant for the covariance function, and that sigma x is your new covariance matrix. No math to be done whatsoever. Similarly, it's really easy to condition. And it might be clear why we need to do conditioning, right? Given the value, one value in our multivariate normal, what do we expect some unobserved value or the next value to be? It's not quite as easy. It's not as much a matter of pulling out individual values, but you can write it down in closed form. There's an analytic solution to it. Okay, so there's a conditional mean. So it's the marginal mean plus some other term, and the conditional or the marginal covariance minus some other term that we can easily calculate. Okay, so we can condition and marginalize really easily. And the reason we want to do this is that we're going to generalize the multivariate normal to not just contain many, many elements, but contain infinite elements. Okay? So what we're going to have is a thing that we call a Gaussian process that, rather than having a mean and a covariance matrix, has a mean function and covariance function. Right? Because you can think of functions as sort of being generalizations of arrays. Right? If you had an infinite number of objects, you don't want to store those and access them like a dictionary or something. You'd want to create a function that generates the one you need as you need it, right? Because you can't store infinity on a computer. So that's the idea. So this is the textbook definition of a Gaussian. An infinite collection of random variables, any finite subset of which have a Gaussian distribution. So it's an infinitely large Gaussian, and anytime you take any subset of them, you just have a regular multivariate normal of whatever that size is. You can see where that marginalization thing comes in, right? Because you'll never want to deal with all infinity of them. You'll just want to deal with the ones you've observed or the ones you're trying to predict, never all of them at once. Okay, so it's kind of yet again, statisticians have named things poorly. And so it's not non-parametric implies no parameters. It's actually we have an infinite number of parameters. But a better way of thinking of it is that the number of parameters, the effective number of parameters, scales with your data. It means bigger models, more data allows you to build a bigger model. Smaller data allows you to build a smaller model. And that's usually a good thing. You don't want to build small models with large data. It's kind of dumb. Similarly, you don't want to build a model that's too big with lots and lots of data. It's the bias variance trade-off, sort of, right? Okay. So this is it. A couple of things to notice is that what we're doing here is we're modeling functions now, right? These are functions. So every realization of a Gaussian process is not a set of numbers, it's an entire function. So we're going to model this underlying function of spawning salmon or marathon finishing times or age effects of some disease. We're going to model the function directly, not its parameters. And in particular, the covariance function, the realization of a covariance function is a covariance matrix. So you pass the function a certain number of values, and it returns the covariance matrix corresponding to those values. So the most important thing about creating Gaussian processes is figuring out what your covariance function is going to be. And depending on the one you choose, you can fit different types of functions. So for example, if you pick a Gaussian process prior that has a quadratic, it's called there's lots of names for this one. Sometimes it's just called the Gaussian covariance function, which is kind of misleading. Exponential quadratic is what we call it in PyMC. It's got one main parameter, which is a length scale, which determines kind of how far you have to go away between 2 points to make them more or less independent. And you kind of get these, sort of smoothish lines. So this is a prior, right? No data. This is sampling from a prior with a Gaussian process with a quadratic, exponential quadratic covariance function. Another popular one is the Matern function. It's a little more flexible. You can see it's a little more jagged. So it's also got a length scale, but it's got this parameter that's usually fixed to some number like 1/2, 3/2, 5/2. And it determines kind of how rough it is. So if you have something that changes potentially very quickly over small scales, this can be a good one. You can use it to model things that are periodic. Cosine covariance function. Okay, there's a whole suite of them. If you go into any of the packages that do GPs, most of them will come with a library of covariance functions. And these covariance functions are just they're basically just kernels, if you're familiar with kernel models. They're some function of distance, because that's the whole game here, right? Remember the covariance between x and y and that first bivariate normal? That's kind of where the power is here. It's kind of what does this point tell me about that point? Then there's the mean function. We don't pay a lot of attention to the mean function. It's a function that generates mean vectors. And we'll actually usually just set this to something simple like 0 or a constant or a linear function, maybe for the growth term in that salmon spawning example. The reason is that it turns out that the posterior Gaussian process doesn't involve the mean, which seems a little weird, but it's true. What it is useful for is as prior information. You can consider the mean function as a prior guess at what that function might be, because wherever there's no data, whenever there's no data in a Bayesian model, what does it do? It shrinks towards the mean. That's because that's the only information you've got. If there's no information in your data, everything's based on what your prior assumptions are. And so for something like a growth curve, you could assume that it's just, okay, in the absence of information, salmon just keep growing till infinity. Okay? All right. So what I'm going to do is draw from a prior Gaussian process. So these are priors over functions. Another definition of Gaussian process is a distribution over functions. So rather than a distribution over values, it's a distribution over functions. So every realization is not a number, and sometimes this presentation is a little confusing because of this. All I'm going to generate it kind of point by point, but I'm going to generate functions from this prior. And you can do it point by point, which is how I'm going to do it. You don't have to. So here's the prior. It's got a 0 mean and a quadratic exponential quadratic covariance function with length scale 1. And so it kind of looks like this, and that's just kind of a standard deviation, 2 standard deviation band, okay? And what I'm going to do is just pick an arbitrary point. I think I'm going to pick 1 or something like that, and I'm just going to draw a value. And this will be unconditional because there's no points existing right now. And so the code is down here. So we go into NumPy, draw a random normal with the scale, whatever our scale is, at 0.1, and we get some number, right? It'll be obviously different every time. So in this example, this is what happens, right? And so we're going to assume for the moment this is a prior, so there's no observation noise. So that's our point. That's one point in this drawn function. The next point I draw has to be conditional on this point. So I'm going to draw from a conditional distribution now. Remember, conditioning is easy for normals. So there's a conditional function here. I've implemented it. It's just that conditional function that I drew before. It's no magic. And I pick arbitrarily negative 0.7, draw a conditional normal, and it's right there. Okay? And so you can see we're kind of, building a link sausage here, right? And you can see we're sort of carving away, and we're going to get, you can see already what this line's kind of going to look like based on what our covariance function is, right? It'll sort of look like that red line more or less. And in principle, we could take we could take infinity points if we had the time. We don't need to characterize it. But that's just one random draw. Here's 4 more from the same function. Okay, so these are just draws from that prior. So that's a prior on whatever we're trying to model. Okay? We convert that into a posterior once we've seen some data, and we need software usually to do that. So questions about the prior and the GP prior? I'd be surprised if there weren't any questions.
So you started off with, I guess, what is like uniform?
It's not even uniform. It's a normal with a mean of infinite normal, mean of 0 with this covariance function that describes a bunch of covariance matrices between any number of points. And
then did you choose uniformly the x's?
I choose them arbitrarily. I would. So if I were to draw, if I wanted to generate a bunch of them, I'd do NumPy linspace 0, 100 and just draw a line. I would do it all at once. I wouldn't do it I did it point by point for kind of illustration's sake.
But each time you put one point, that affects the possibilities of the point next to it, but not so much the points far away.
Correct. Unless I had a really big length scale. If the length scale was really big, it means that things are highly correlated even far out. And so you'd get these big, curvy things that are like this as opposed to, that kind of.
But if you were like, I'm imagining if you like picked the points linspace and you went in order versus if you like chose randomly throughout, you'd get different.
You still get the same, eventually you want to get a line, right? Something that represents a line. So you wouldn't pick randomly. There would be no reason to pick randomly.
Is it almost like some type of?
We're just doing conditioning.
Brownian motion or is it?
You might be modeling Brownian motion. We don't know. This is just a prior. You wouldn't use an exponential quadratic to model Brownian motion. That Matern would be closer, right? Because it was very jagged. The functions I was drawing were not very jagged. Yeah. Any other questions? Yes?
So I'm trying to think if there's a difference in practice. Like once you put this in a numeric situation, between thinking about it just as like every point in your discretized function is its own random variable, and there's some covariance between your random variables, so that you just have like a 1,000 parameter Bayesian model, and you're fitting that.
Yeah.
Is there something that you lose by thinking about it in that sense?
No, because again, you can marginalize condition whatever way you want. The infinite stuff is any point you want to access is always there for you to calculate. But you can't, in practice, all you're interested in is the ones where you've observed data, the ones that you're trying to impute maybe, or extrapolate to. So they're always, because you've got a function, you can always ask for a point. You just don't hold them in memory all the time. Yeah. Okay. There's lots of ways of doing GPs really easily in Python, and they range from high-level to low-level interfaces. TensorFlow probabilities just added them, and they're very low-level. If you like to write TensorFlow, have at it. PyStan they're very low-level too. You kind of have to roll your own. PyMC and scikit-learn are very high-level, right? You just say a Gaussian process. Well, we'll see how we do it in PyMC, but scikit-learn, it's just a class like, random forest or something. The other ones, GPy, GPFlow, GPyTorch, they're sort of in the middle. You have to kind of write classes, which some people like to do and others do not. So you have a wide range of approaches. All right, so let's go back to our salmon recruitment. Now, how would we do a GP for the salmon model that we just fit linear models to? Again, looks like that. The cool thing is we don't have to say that it's polynomial or exponential or log linear or whatever. All we have to do is do Bayesian stuff. So the way it works, just like any other Bayesian model, you specify your model or specify your probabilities, calculate posteriors, do model checking. So we have to specify a prior and a likelihood. And in this case, our prior is going to be a GP. That's the thing we were just manipulating. Our data is going to be Gaussian. You can argue whether or not this data is Gaussian. It works as Gaussian. They're just they're numbers of spawning offspring. Maybe something else is better, but we're going to treat them as Gaussian for now. And the nice thing is that a Gaussian process prior plus a Gaussian likelihood gives you a Gaussian process posterior in closed form. It's a relationship known as conjugate, and there's a whole bunch of examples of conjugate models in Bayes, and this is one of them. So it gives us another closed form way of doing this. So in Python, what we've got to do now in PyMC, we've got to, just as before, specify priors for our unknowns, except this time our unknowns are the hyperparameters for the covariance functions. So this, we're going to use our squared exponential one, the same one I was using before. This is that length scale I told you about, and then we've added another one here, which is like an amplitude. It's a signal variance. So length scale kind of determines how things vary along the x-axis. It sort of compresses it this way, compresses and expands this way. This one, since it's just a value that you're multiplying it by, so it's going to expand on the y-axis here. So we got two unknowns here. We don't have to have that, by the way. It just makes it more flexible. So anytime you add a parameter, you're making things more flexible. So I'm going to use half Cauchy distributions. What's a half Cauchy distribution? A Cauchy distribution is kind of like a normal distribution with really, 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 really long fat tails. It allows the possibility for really extreme values, right? Remember, normal has that attribute where, 67% of the values are between two standard deviations, or within one standard deviation of the mean, and around 95 of them are within two standard deviations of the mean. Not the case with a Cauchy. It's got really peaked, and then it's got really broad tails. And then this is just going to be the positive half, because both of these, because these are scale parameters, they always have to be positive. So we don't want negative values. So it's a good thing to use as priors, because it says we're pretty confident that the value is going to be relatively close to zero, but they could be, it leaves open the possibility for really extreme values, so you're not binding yourself into a corner. Okay? And so here's our exponential quadratic. There's rho, there's eta, and then here's my mean function. Remember I said we could set the mean to anything, and here's where I'm putting that linear function, and I'm just going to take the rise over the run of the data, which is kind of cheating for Bayes, right? Because I'm using the data to specify the prior, but it really won't matter. You could easily have just put 0 there. And then what we're going to do is pick a marginal Gaussian process. So this is marginal because it's this closed form thing. If we've got Gaussian data with a Gaussian process, we get Gaussian. And so all we have to do is optimize that marginal likelihood, that denominator, which we now have in closed form here. Okay, there's the marginal likelihood, in fact. So here's just like if we were building a model, this is the noise. So this is the observation noise. So we're dealing with data now. Not everything is going to be described by the underlying process. So here's the marginal likelihood. This is the equivalent of the regular likelihood in a Bayesian model, except this is the marginal likelihood. And we pass it x, the number of points, because we don't want to deal with infinite points. We're interested in x points. This is the grid of values over which we have observations. And then here are the outcomes, and there's my noise. Okay. And then all I'm going to do here is optimize. So the cool thing is you don't have to do crazy MCMC stuff, although you can. We can just optimize. So find map stands for find maximum a posteriori, which is the maximum of the posterior distribution. So it's just going to hill climb to the maximum value. Okay. If we're interested in the uncertainty of our hyperparameters, then you can do MCMC. We'll have an example where we can do that, but you don't have to. So officially, it's not like fully Bayesian. Okay, and then how do we make predictions? How do we, once we have the values where we have observed data, how do we go back and get other values, like if we wanted to draw the full line? This is no different than in any other Bayesian setup. We use the posterior predictive distribution. So the posterior predictive distribution is how we make predictions with a Bayesian model. And it involves two components. The posterior, this is the posterior we've just been estimating. And that is our epistemic uncertainty, so it's our unknowns. And then there's aleatoric uncertainty, so things like noise and the observation noise. Right, so you've got to incorporate the stochasticity of our data generating process. This is essentially our likelihood here, as well as our uncertainty in the parameters. Okay? And the good news is, don't be afraid of the integration sign. We get this for free as well from sampling from our model. Okay, so all we do is we pass it new points that we're interested in, and it'll give us predicted values after having fit our model. Okay? Just like if you're using scikit-learn, you fit your boosted tree model, and then you pass it predict, and it generates predicted values. This is the same thing here. So in PyMC, it looks like this. So we create this conditional. Remember, we're doing now conditional prediction over some range of spawners. So let's say I want to know everything from 0 to 500. So that's what I was talking about with you. So linear space, and we're just going to predict from 0 to 500. And then, oops, this is out of date. We renamed sample PPC to sample posterior predictive because it's more descriptive. And then we pass it the model, the fitted model, the variables that we're interested in, which is this one. And I'm just going to draw 3 little samples, which we'll see if we go back to our notebook, which we'll do now. Any questions about specifying the model? We're just about to do it by hand here, so. Here it is. All right. All right, so here's the GP. This is just exactly what I had written on the slides. And feel free, this is your hands-on time. You can change some of this stuff if you want to. If you want to play with different length scales, different priors, feel free. And, I didn't do, okay. All right, so here I am going to do MCMC. I thought I had done maximization. We can do both, actually. So the difference here is, so if I do find map, I'm just going to get single values for each of these, just the estimated maximum values. Now I get distributions of values. Okay. Whereas find map would have given me, that value, and probably something up close to 0 for here. And then here's the conditional piece. So now I'm going to draw 3 candidate lines. Okay. All right, and so that each of these could potentially be the true underlying process, and you can see it's kind of interesting because the whole conundrum with nonlinear models is do you believe that there's this weird dip around 350 spawners? Probably not. If you know anything about the biology, there's no reason why that should happen, but the data is the data. There it is. And so some of the lines think it is, and some of the lines think it doesn't. And so you can generate a whole bunch of these. So I can go back in and generate 100. And you can see here that, basically every line is kind of like a vote for the true posterior, right? And most of them are kind of passing it by, but there's still uncertainty there, right? There's still uncertainty. Whereas if we had collected millions of points, it would be a line basically through the data. Okay. These are draws from the posterior without any observation noise. So these are what we think the true line is. We can also draw ones with prediction noise, so including the noisy bit. So this would be if we wanted to predict new observations. Here we're predicting the underlying line, which is subject to stochasticity. And now you can see, now you should see most of the points within kind of the band that you get. Okay. So if you wanted to generate new predicted observations, this is what you would use. If you were interested in the latent process, so to speak, you would leave the noise out. Okay. I'll skip this exercise, leave it for you. So what happens if we wanted to project outwards? What happens at 600, 800, and beyond? Right? Well, if we know something about biology, you start hitting, starting to curve because there's density dependence, right? It starts to, too many salmon, it gets crowded and they can't produce as well. But just like anything else, you have to be careful about extrapolation with Gaussian processes. Because once you get far enough away from the data, what happens? What does it start to look like if you have no data? If there's no data in a Bayesian model, what does it rely on? The prior. So go back to the prior. Remember what the prior was just a straight line like this. So it'll say salmon all the way up, right? So you only want to trust an extrapolation depending on how big your length scale is. So if your length scale is pretty long, you might be able to trust a bit of an extrapolation, but other than that. Okay, there's an example on the PyMC documents of the CO2 data, right? That's going up and up and up. And when you extrapolate on it, it goes down again. And say, oh, we're saved. It's all going to go down in a few years. But it's just because we had a 0 prior mean, and so it goes back to the mean when there's no data left. So you have to be very careful about extrapolating. How are we doing on time? Half an hour? Cool. Pretty good. Questions?
Can you say again what you mentioned about including versus not including the noise?
Yes. You may be interested in two different things. One is, what do I think the underlying reproduction curve looks like? Sort of your expected value, right? But there's noise. Like these values down here are probably due to noise, not due to a process, right? So if you don't include the noise, all you're getting is the estimated posterior of that underlying function that you're trying to estimate. If you add noise, you're including how far away from that expected value could observations be, because we've also estimated sigma, which is our normal white noise process, essentially, right? And so that is better for predicting observed values. Where could it, how high? So in other words, if we observed a value down here, then something's wrong. Something's wrong with our model then. We've underestimated the noise, or we've estimated the wrong model. but all of these points are comfortably, well, not necessarily comfortably, but well inside. There's always a point that goes below it, so it's contained inside of this sort of envelope of uncertainty. So this includes stochastic uncertainty as well as parametric uncertainty. So are we interested in estimating the function, or are we interested in predicting new values? This is for predicting new values. Okay. All right. Yeah. So we saw this. Okay. This is this one's on the log scale. Sometimes nicer to look at it on the log scale, but that's the same thing with the stochastic noise on there again. Okay. All right. On to the next example. So you could accuse me of being all textbook on you, giving you an example that's normal prior, normal data. Good? Yeah. All right. Sorry about that. Yeah. All right, so what if
for a shot. This is these are our own that we brought for the event because the building didn't have AV set up for these rooms. So, all right,
that looks a green light at least, rather than red.
Promising.
You hearing me?
Yeah, you're good.
Okay. All right. Turn it off and on again. It works every time, doesn't it? Okay. What did I say? Oh, yeah, counts of disasters. So every year, mining collapses and things. And so these are count data. Typically, you don't model count data with normal distributions. One, because counts are discrete rather than continuous, right? And also, there's usually a mean variance relationship. As the mean goes up, the variance usually goes up. So, and what I've just described are characteristics of a different distribution called the Poisson distribution. So you'll often see Poisson distributions used to describe count data. So our likelihood is going to be different now. So we're going to assume that our data are Poisson distributed, and our prior is still Gaussian. So Gaussian plus Poisson, we can't do our nice marginal GP now. We have some sort of transformed Gaussian process. So we've given ourselves a little bit bigger of a challenge. So for that, we have to use a slightly different kind of Gaussian process. And we call this a latent GP. Latent means there is a Gaussian thing in there somewhere, but we're going to transform it so that it's the mean of a Poisson, because the mean of the Poisson has to be positive because it's modeling counts, and you can't have negative counts. So everything looks very similar. It looks the same up till here, actually, right? Except I used exponential inexplicably rather than half Cauchy. It probably doesn't matter. As an exercise, you could go in and swap them out and see that it won't matter. Other than that, it's the same, except now rather than marginal, it says latent. Okay? And latent just says there's another step. There's going to be a different posterior distribution. You can't just use the closed form way from before. So the transformation we have to make is take this prior, which is this GP prior, which is Gaussian, that can have negative values. And how do you make something negative positive? Take the exponential of it, right? So inverse log transform. So exponential of whatever f is, it'll guarantee that all your values are going to be positive. So we've done away with that boundary. In PyMC, those sorts of transformations we wrap in a deterministic node. So this is just an arbitrary deterministic transformation. And then we use a Poisson likelihood rather than a normal here. So our likelihood is Poisson now, where the expected value is lambda. And then here are our disasters here. The year is here. And it expects a 2D array, so we have to add an empty dimension. All right, so that's the big change here. Is rather than marginal, we have a latent with a prior. Okay, and so it'd be the same as before. Call MCMC on it, and let's give it a try. Okay, here it is. Mining disasters. And it's a small data set, so it's just right here in one of the cells. Oops, let me restart the kernel. I must have been messing around with this before. All right, there's the data. So this part's the same except for the latent part. So there's our GP latent, our prior, Poisson, and PyMC's got most of the important NumPy functions that you'd want, but they're buried inside of PM math, and that's because they're actually Theano functions. So you want them to be Theano functions whenever you can. And then we'll sample. Right. Don't think I need this actually. And by default, PyMC will use half as many cores as your machine has. So on this, it will use 4. So I'm just telling it to use 2, just so I don't want to use that much. Although as many as you can is best for model checking. Nothing like watching MCMC run. Yeah. The next example we're not even going to do hands-on because it takes a long time. So. Okay. And you do get warnings. Divergences, so I told you about gradient-based MCMC, and so it tries to follow the gradient of the posterior. Sometimes it diverges and goes off into a weird place, and it reports how many divergences you get. If they're just a couple, it's usually okay. There are diagnostics in the RVs package, which is being used to plot these things that you can, these are probably okay. I've done this model enough to know, but okay, and so now, so what we did in the example that we use for PyMC in general is what we use this for as a change point model, where we say there's an early mean, some regulatory thing happened in here to change safety or something, and then there's a lower mean down there. And so a very simplified regression, piecewise constant model, very simple model. This is saying this allows for, arbitrary changes in the underlying risk, if you like, for a disaster. And you can see that there was sort of a step in here, but it could be non-constant, who knows? Yes?
I mean, if I looked at it and for some reason I thought, hey, it goes up in the late 1930s, maybe I worry that that's just overfitting noise or something. Is there a way to change the prior to force it to be a little smoother throughout?
So because we've done MCMC, it's taken that uncertainty into account, right? So these are the posterior. So here's the length scale. So if the length scale truly is up around 11, then it will be smooth. And if you zoomed in on this, you'll see some of those lines are going to be almost, change over a much longer period of time, whereas others don't. So that uncertainty, that's the nice thing about this, is that there's no overfitting here. It's just that it's because a realization is a function. So you can't add or subtract parameters from an infinitely parametric model. So not that you can't overfit a GP, but it's pretty hard. Yeah?
Why do you have to use latent?
Because the marginal, you can only use the marginal when it's that conjugate normal, because it makes the posterior closed form. And so all you have to do, so that big integral that's at the bottom of the Bayes formula is closed form. And you can actually just maximize that to get your hyperparameter values. So it's a lot easier. There's no conjugacy involved, and so you've got to build it. So what it does is it builds a latent GP and then transforms the normal with and uses a Poisson likelihood. And so it's just a harder. So you can't specify it in closed form. Basically, that's. So the model took a little bit longer. It's a little bit more costly computationally, but structurally they're different. The thing that's being optimized is different in a marginal model versus a latent model. Yes.
But you could choose to use a Gaussian prior as well, even for that distribution, even though it follows a Poisson distribution.
A Gaussian process prior. The Gaussian process prior is on the log of the. So we're modeling. If we go back up to the model, we're modeling the log rate essentially. So we're modeling the Poisson rate. So that's the rate of accidents, and the Gaussian process describes the log rate of that. So if you take that positive value and you take the logarithm of it, you'll get something that's on the real line, and you say that that's normally distributed. So it's going to be Gaussian, but it's the latent thing that's Gaussian, not the observed thing. Anybody else?
Is there a way to do something like over disperse Poisson if one thinks that the dispersion isn't really linear?
Yeah, so hold on, while I'm talking, I'll change the priors and see what difference it makes. So there are still choices to be made about the likelihood and the priors, like I'm just testing now. What's your name? Sorry, Alan. What Alan was suggesting is that the Poisson distribution may still not be suitable for counts because sometimes counts are over-dispersed, which means so the Poisson's only got one variable, lambda, and it describes the mean and the variance. Well, it's not all. Sometimes you get situations where the mean and the variance aren't the same, and so a negative binomial distribution is a generalization of that that allows for over-dispersion. So that's a slightly more complicated model. So you could try that and do model selection to see which one's the best. I usually start with the simpler model, check the goodness of fit, and if the fit is okay, I just leave it alone. If the fit is poor, then I'll make it a more complicated model. I think it's running even slower with the half Cauchy. And all I'm going to do is do another plot of the posterior salute and see if they're any different. Fewer divergences. So it looks like the length scale is a little bit more sensitive, which makes sense. The Cauchy prior has a little bit longer of a tail. Let's see what kind of a difference that makes to this. So there, see, this one is a little flatter. So it looks like it's a little smoother. Okay, and you can do goodness of fit checks to see which of these is preferred, but it's not overly sensitive. Okay, back to this.
The red lines are just the means of each sample.
Pardon me?
The red lines in that
The red lines are draws. They're
draws.
posterior draws. Yeah.
of the mean.
I haven't done any mean. It's the posterior draw of the latent process, the estimate of lambda over time. Okay. All right, and so we have posterior hyperparameter estimates, which we just saw. Okay. Another non-normal model that I'll quickly go through. This one won't have a hands-on component. So this is from, I used GPs in practice for this. Before I was in baseball, I was a biostatistics professor at Vanderbilt, and we were studying infectious disease dynamics. And one of the things about measles is that people show up with symptoms of measles, but they sometimes don't have measles. They'll have rubella or something else. And so there's a bias having to do with detection bias. Sometimes you overestimate or underestimate the numbers of cases. Here we're talking mostly about overestimation. So this is confirmation bias. So you test somebody out in the field. You give a quick response based on the test that you do there, but then you lab confirm it to make sure. And some of the lab confirmations come out negative. And so to properly model it, you want to correct for that. And so this is exactly the same as the other one, latent GP, exponential priors. And now I'm just using a binomial, right? Because this one is out of how many potential cases, how many were actual measles cases, right? So now I'm estimating the confirmation bias in measles. And it looks like this. Age, this is the most frequent application for me for GPs is in these sort of age-specific things, because age is almost notoriously nonlinear for a lot of things. So you can see it goes down for kids and then goes back up for some adults, and then the cool thing is that you get some uncertainty out here for elderly folks because there are much fewer cases. The size of the points represents the number in that age category. So tiny points here, bigger, more cases in here, right? So very useful. And often I do this. You can roll this into another model. This could just be a component of this is a component of a larger model modeling the dynamics of measles. This is just a correction for the bias that is age specific, and it's important to take that into account. And here again, how would you model that parametrically? It would be difficult. You'd have to do some polynomial thing. Okay. All right, about 15 minutes left. So, so I've shown you the good news, the things that Gaussian processes can do. Now the bad news. And we're in the age of big data. Gaussian processes are not typically good for large data sets. And the reason is you have to look at the posterior distribution, or the posterior Gaussian process. So this is the posterior of the covariance function. So K star means posterior covariance function. And it has a nice closed form like we saw before. This is the marginal piece. But if you look closely, you take the covariance function evaluated at x, which is the data, and you do something to it, and then you invert it. So you're inverting a x by x matrix. So if you've got 1,000 data points, it's an 1,000 by 1,000 matrix inversion. And it quickly is, it's very hard to do. It's cubic in compute time and quadratic in memory. And so it really, large models take a long, long time and often croak. So what we do is we approximate instead. So what we can do is rather than have a full prior based on all the observed data, we get sort of representative points of the data and use them as what they call inducing points. And we have a sparse approximation to our prior. So we have these things called pseudo inputs that are of size m, which we presume to be much smaller than n. Like you'd pick, for that measles example, you might pick 5 or something like that. So it reduces the number of matrix eigenvectors that are used to fit the data, essentially. And so it reduces the expressiveness of the GP, but it sometimes doesn't matter. So the example I'm going to use is that Boston Marathon data set that I briefly flashed up at the beginning. So 2015, over 26,000 finishers. It's crazy that many people are running marathons these days. These are the really fast ones too, so you have to qualify for Boston. So to fit a regular GP to this data, you'd have to invert a 26,000 by 26,000 matrix, which good luck with that, right? So that's what the data looks like. So what we want to do is we're after is the expected finishing time over all of the age groups. And so what we do is just add one additional piece here, which is a set of inducing points. We'll call them XU. And you can specify them yourself. For data this dense, it doesn't matter very much. You can probably just say 1, 2, 3, 4, 5, etc. But PyMC has a nice utility function that picks them using k-mean. So it just does clustering along the line. And they're not useful clusters in the sense of clustering things, but it's, it'll find good places to situate points. And it's more important when things are actually clumped in different places. Other than that, it's all the same, right? Except now we're using marginal sparse. Unfortunately, this does not work, at least in PyMC3, in the latent case. So if you've got large data that is not Gaussian, you're kind of out of luck. You got to roll. Not that you can't do it. We just don't have these high-level classes to take care of it. So I'm going to pick 20 inducing. Oh, it says 20, but I actually took 10. And then everything else is the same. Marginal likelihood, this looks exactly the same, except we're also passing XU here. And it will expect that anytime the GP itself is marginal sparse. It'll say, where are your inducing points? Okay, and there are a lot of different ways of doing these inducing points. The default, I think FitC is the default. I just wrote it out to be explicit. It stands for fully independent training conditional. They're all just different methods for reducing that eigenvector size. And different methods work better in different situations. It's always best to fit a couple of them and see which ones turn out better. And ta-da, looks like that. And this doesn't run in too long of a time, but I don't have a hands-on for this because our last example, which is what we'll go into now, is also going to be sparse. So we'll get a chance to do it by hand as well. Okay. All right. The last generalization we'll do, and this is a really useful bit. I use this a lot, is doing multidimensional Gaussian processes. I don't mean on the input side. Obviously, it's infinitely dimensional, but the output. So up till now, we've been modeling univariate time series mostly, or age series. Sometimes we want to do things like spatial stuff. And I use these a lot in the baseball applications. But the example I'll give you is from a textbook. This is from a geology textbook. applied geostatistics from back in the late 80s. These are just samples from various locations on a landscape, and there are like 3 substances. In the textbook, it doesn't even tell what the substances are, and there are measurements of each. So it's just V, U, and T. And XY location, so our inputs are going to be XY, and we're going to model one of the substances here. The data kind of looks like this. So it looks like what they did is they went in and had a grid, and then wherever they found, got some threshold value, they went in and sampled more, right? So they did sort of search strategy. So around here, so here where there could be pockets in here where there's yellow, but they didn't find any. So it's sparse, relatively sparse data, spatial data, 2-dimensional. And so what we're going to do is come up with there should be a true underlying distribution of substance U that we're trying to estimate here. And it's remarkably easy to do that. This looks very similar to what we were doing before. I'm using a slightly different covariance function. I'm using the Matern. Remember, it's the jaggedy one. I figured, with something like this, there could be a little bit of roughness in the underlying function. But the important thing is, you may have noticed before and chose to ignore that there is always a 1 beside as the first argument in the covariance matrix, or the covariance function, and that specifies the dimension. And so if you want to make it 2-dimensional, you just put a 2 there. And the only constraint on that is that it now expects 2-dimensional inputs. So kind of like declaring a layer in TensorFlow, and you've got to have input dimensions. That's the input dimension. Okay. Everything else is the same. There's our marginal sparse again, our inducing points, which come from k-means, and then I'm not going to do MCMC. This will take a little while. So yeah, that and that. And then after I'm done, right, then I want to evaluate it on a full grid. So I go in and I take a 30 by 30 grid, regular grid, and I'll create a heat map at the end of it. So I just pass that big Z in there. Okay, so let's do the last example. Multi-dimensional GP. The marathon one is in here, by the way, I think. If it's not, I'll make sure it's uploaded after I'm done. Clear all outputs. Okay. Looks like we're modeling V. We're modeling substance V. Okay, and then here, I didn't actually show you find map before, but there it is. And it's just doing optimization now because this is a marginal. It's fast. So now we won't have distributions for the unknown parameters. They'll just have maximum point values. So you are sacrificing uncertainty in the hyperparameter values. But we are sampling from the posterior predictive. But again, it's going to be conditional on one value for the hyperparameters. Okay. Let me get this. And so you can, I did 30 by 30. You could do 100 by 100 and get a nice smooth one. It looks better. Whatever you need. All right. We're almost at the end here, so I will wrap it up. And this is the same as Kriging. If you've done geostatistics before, if you've done Kriging, you've already done Gaussian processes because they're the same thing. All right, there's plenty more where this is just to whet your appetite, give you the basics. As I said before, you can do classification with GPs. That's when you use a latent, right? And that would be like a Bernoulli or a binomial thing where you're classifying something as 1 or 0. The kernels, the covariance functions, are additive and multiplicative. So if you have something that is, say, periodic, but also, like the CO2 levels in the atmosphere, you can combine a linear kernel with a cosine kernel and model components of things. There's a really good example in Gelman's textbook, Bayesian Data Analysis, where they model births at different days throughout the year, and they use a seasonal component and a component for holidays and a component for weekends and all of those things. Automatic relevance determination, you can do sort of an automatic model selection thing if you've got a lot of variables and you can have a different, what this involves is having a different length scale for each variable. Bayesian optimization, if any of you are machine learners and you one of the best ways to select hyperparameters is to use Gaussian processes, because there's some underlying surface that represents how well your deep learning model performs over different values of your hyperparameters, and what you want to do is optimize that. And so you can model that function directly using GPs. And then you can show that GPs are related to all these other, you can show that they're related to support vector machines. If you take a neural network with a hidden layer with an infinite number of hidden nodes and put normal priors on the weights, it's a Gaussian process. So there are links to other things. So you can make deep Gaussian processes and so on. The advantages, I hope I've made clear. It's flexible. You get probabilistic predictions, which are nice. Interpretable hyperparameters, I think they are. Maybe you don't. Length scales, it kind of shows how over what scale things vary over. And it's relatively easy to automate. And the limitation is that it's, as we saw, scales poorly with large data. But if you look in the gPyTorch package, the creators of that package have come up with a new method called black box matrix inducing. And it calculates exact GPs for very, very large data sets. And what it does is it utilizes GPs and parallelizes the matrix inversion. And it's very fast. So I use that a lot too. So you may want to stray away from PyMC3 if you've got larger data sets. So other than that, I want to thank the PyMC3 team. This is kind of the current active membership. The actual contributing number is a lot larger than this. In particular, Bill Engels. Bill Engels pretty much single-handedly developed the GP capabilities of PyMC3 over 2 Google Summer of Code summers. And so absolutely amazing stuff. And that's why it was so easy for me to do this for you today without having to dig too deeply into the internals of PyMC. And with that, I'll wrap it up. And I got a minute or two for questions. 3 minutes, in fact. And then I'm going to the airport. So thank you very much. And I'm happy to take questions. If there are any.
So when you have like a large covariance matrix that you want to invert, you said you're doing sparse approximation. Mm-hmm. I was just wondering, is that like a low rank approximation?
Yes, yeah. So you pick those like 10 points, and then you're calculating, you essentially have 10 eigenvectors. So it collapses the information in the data onto those 10 points. And so you're inverting a 10 by 10 matrix instead of a million by million.
Yeah. And you use like a QR or SVD?
So the different fit-C will do something like that. Each one does a slightly different way of doing it. I didn't want to get into the methodological details, but there's a good paper that summarizes, if you just look sparse approximation, GP, there's one that summarizes each of them and how they go about doing it. And some will like underestimate the noise, and then some will bias things on the hyperparameter side. So at different ones, there's always trade-offs when you do these shortcuts, and so it depends on which trade-off you're willing to make. But yeah, and back here.
Yeah. So for multivariate data sets, and let's say for example, you have missing values.
Yep.
What would be the best case scenario? Would you like impute the data or throw out those data points?
Yeah. No, I never throw out data points, and Bayes makes. Because you have that posterior predictive distribution, it makes it really easy to impute them. You can do it automatically without having to throw out any data. So this does them automatically, right? And anything you don't observe, you can include as a variable in your Bayesian model. And by the fact that it's a GP, if you have an unobserved X, it will impute that for you if you just ask for it in the conditional after you've fit the data set. Where I wouldn't do it is if it was way outside the data, like I said, with the extrapolation problem. But anything near the data, you should get a really good imputation. And that's sometimes how this Kriging, that's really what I was doing with that spatial surface, right? Is I was interpolating values using this unknown function estimate. Okay, thanks everybody.